This is Tech Math 2, and we're currently in section 10-4. And section 10-4 has to do with using radians to work problems. If I can spell radians. I think I did okay. All right, so we do have a formula, and if we remember that the circumference of a circle is pi d, right? Pi d, or it's 2 pi r. So now if I look at a circle, I got myself a circle, and I want to know how far is it around for some amount of area. What is that sector of the circle? What is that little bit there? So my that's going to be pi theta, where theta is in radians. So if I went all the way around the circle, my theta would be 2 pi. So 2 pi would be 2r, whatever. I'd be the whole thing, 2 pi r. So, but my radians are going to be, whatever that theta is going to be that sector. I can also come up with an area. So I got some area of a circle. The area is 1/2 pi r squared, right? Pi r squared. No, it's not. That's what the front row is for. Is pi r squared. All right, and pi could be 2, right? It could be, I could have a d there, so it could be pi over 2d for the diameter squared. I could do that too, right? So now I ask myself, if I have a circle and I just got a piece of it, and I want to find that area. What is that area going to be? And so the area of a sector is going to be 1/2 pi, not pi, r squared theta. 1/2 r squared theta. There we go. And then I say, well, that looks kind of bad. Who made that one up? Well, if I had the whole circle, theta would be 2 pi, right? So the area of the whole circle would be 1/2 r squared times 2 pi. The 2's go away, and I'd be back to pi r squared. And oh, isn't that lovely? So we don't prove anything in Tech Math, but every now and then we show something. So that means I now know the length of an arc, and I now know the area of a sector of a circle, and now we get to apply those things to problems that we have to do. All right, well, we'll start off with number 1 just to say we did. From a circle of radius 12, radius 12 something, 12 inches. Notice that there's 3 significant digits, so we better have our answers to 3 significant digits. Find the length of the intercepted arc when the central angle is 2 pi over 3 radians. 2 pi over 3. Now, the whole question is written in English, right? Okay, so that's a good thing. So 2 pi over 3, where would that be? That would be somewhere over here, right? Like that. Because 2 pi over 3 would be 120 degrees, would it not? 120 degrees. Not that we care, because we're solving the problems in radians. We'd sort of like the picture to be right. And it would have been a good idea to put the radius on the x-axis, so it would, that would have been a good idea too. We didn't do that. Okay, so the length of the arc is, did we forget the formula already? R theta. R theta. And so we're looking for that arc. 12, 2 pi over 3. 3 goes into 4, 2 goes into 12, 4 times 2 is 8. 8 pi inches. Do we like pi inches? Probably not. So we take out our calculator. 8 times pi. 25.1. I have three significant digits. 25.1 inches, and we call that our final answer. And see if I can make the point look better. All right, well, that was okay. Is that okay? Yeah. One equation, one unknown. Let's see, could I do it differently? No, can't do it any differently to make it easier. Look at number 3. Find the area of the sector of the circle in exercise 1. Well, isn't that convenient? I hope I remember that. All right, so this time we're going to do something cool and put the radius there, and I have 12 inches. And I'm going to be over there at 2 pi over 3. And I'm looking for the area of that. Okay, so area is, maybe I remember this one, 1/2 r squared theta. Is that right? All right, so 1/2 12 squared times 2 pi over 3. Right, the 2's go away, 144 over 3 pi. I look at 144, I see that it is divisible by 3. 4 plus 4 plus 1 is 9. 3 goes into 9. So 3 goes into 14 4 times. 3 goes into 24 8 times. So 48 pi inches and squared, and that would be really bad notation, so we're not going to do that. Inches squared. And then we say, well, that doesn't do much for me. 48 times pi. And again, I want only 3 significant digits, so I'd call it 151 inches squared, even though my calculator has 150.79644474. But I'm not gonna keep that many significant digits. I'm just gonna keep 3. Okay, questions about that? Anybody bothering to look in the back of the book to see if I got it right? Didn't think so. No, don't look. Don't look. No, not doing it. If you haven't done it yet, there's no reason to do it now. All right, so we'll try 7. That looks on the weird meter, that looks weird enough, right? So I need 2 circles. Okay, so there's 1 circle. There's 2 circles. There we go. That better? Okay, so I got 2 circles. I have radius 1. And I have radius 2. Radius 2. And I have theta between them. Isn't that great? That is just so marvelous. And I imagine, I haven't read the problem yet, but I imagine I'm kind of trying to calculate what that area there is. Is that what I'm trying to do? For the new students in the class, this is Ben. When he shows up, that means the last student has in fact arrived. We never pick on Ben though, because we never do that, ever. Not ever. No, constantly. Not But whatever, yeah. Okay, so where was I? Theta. Okay, back to, yeah. He needs lots of help. Anyway, back to our problem. So theta is pi over 6, which we also recognize as 30 degrees. And obviously mine is more like 45 there, but that's okay. Pi over 6. And R1 is going to be 3.00 meters. So I have 3 significant digits in the problem, which I will use. Pi over 6 would be, we don't say that we only have 1 significant digit. They would say we have many. So we're limited in significant digits to my radius, and that guy's there. And the issue is, what is the shaded area? All right, so maybe, it's been a long time, we remember that the area is 1/2 r squared theta. Okay, so that's what we're going to use. And so we're going to say the area of the shaded portion is the area of the all theta all, minus the area of theta with just the little r. So we'll call, instead of calling it theta all, we'll call it theta with r2. So we're going to take the theta of everything that theta would be an area, and then we're going to subtract the little guy. All right, so I got 1/2 r 5 squared pi over 6 minus 1/2 3 squared pi over 6. All right. Well, that doesn't help us any, right? 25 doesn't look much like a 5, but good try. 25 pi over 12 minus 9 looks like 3 pi over 12. 3 pi over 6? 3 pi over 6. No, 3 pi over 4. All right. Any complaints? No complaints? All right. So that's a 9, right? 9 over 12. So 9 subtract from 16. 16 pi over 12. And I'd probably just go up here and put that directly in my calculator. I probably wouldn't do any of this other stuff. 4 goes into both of those. 4 pi over 3 inches, meters squared. And again, we probably wouldn't leave the answer that way. 4 divided by 3 times pi. And we want 3 significant digits, 4.19 meters squared. And we'd probably use that as our final answer. If you left this on your test, I certainly wouldn't mark that as wrong. That wouldn't be a good thing to do. Unless it was Ben, right? Yeah. Unless Ben hadn't missed anything to that point on his test and was heading for 100, then that would be a minus 0.1 because he didn't give me the right significant digits. Absolutely correct. Thank you for correcting me on that. Number 9. Pendulum. Okay, so this thing is swinging back and forth. I like that. Of length 5 meters, and again to 3 significant digits, swings through an angle of 6 degrees. All right, so it's going to swing through an angle. So, yeah, so I like that, 60. Find the length of the arc through which the pendulum swings in one complete swing. Okay, so that's weasel wording telling you that whatever your answer is, multiply it by 2 because it's got to go all the way over and all the way back, right? All right, so the length of the arc is r theta. All right, I know what r is, 5 meters, but I don't know what theta is. So I have pi radians in 180 degrees, which is going to be equal to x radians in 6 degrees. So the 6 goes on top, the 6 goes into there, so x is going to be pi divided by 30. So my pi divided by 30 will be my radians. And now 5, so a pi over 6 meters. And then we'd say, well, that's not really what we want. Pi divided by 6, and we want 3 significant digits. So we change it to 0.524. 524 meters, and then we almost fell into the trap because we got to multiply that times 2 because I want a complete swing, times 2, but you guys would have told me that, right? And so 1 complete swing, 1, spell 1 complete swing. 1.05 meters. Wow, that big? Really? Oh, 5 meter thing? Yeah, that's fine, right. Okay, that was 9. All right, so what do we care about? Gasoline cars, airplanes, or flywheels? I guess we'll care about 15. The angular velocity of an airplane propeller. Oh, that sounds cool. Sounds like a Physics 1 question. So the angular velocity of an airplane propeller is increased from 1800 RPM to that's revolutions per minute, 1200 RPM in 10 seconds. Find the angular acceleration. Okay, well, we know that if this were linear, acceleration is a constant, 9.8 meters per second squared, or 32 feet per second squared. And velocity at times t is going to equal whatever my initial velocity is plus my acceleration times t, and my position at times t is going to be position naught plus my initial velocity at times t plus 1/2 that acceleration t squared. Now, why do we know that? Well, we know that because in chapter 22 of the book, that's what we solve. So that's how we know that. Now, if I have theta, then which I do in this case, then I say my angular acceleration is going to be a constant. And then I say my angular velocity, that's an omega in case you're wondering, at times t is going to be omega naught plus alpha t, and my position at times t is going to equal my position naught, and these things are in radians per second and radians per second squared, plus omega naught t plus 1/2 alpha t squared. And that's where we're getting the formula that says alpha is change in omega, change in time. We're getting that from these equations. All right, well, that's interesting.
What was that last part of the last? We're not seeing whole screen.
Bummer. Let's say you're not seeing, you get the alpha, huh? What they do, move my, it's there, right? That's not even there. So quit writing on the side. All right, here we go. View, zoom. There, is that better? Yeah, you can see alpha t squared there now. All right. Well, that's a horse of a different color. Anyway, the issue is we got these things called revolutions per minute. And those are doing us absolutely no good. And we want them to be in radians per second. That would be good. Radians per second would be good. All right, so dimensional analysis says if I have revolutions per minute, and I multiply that by 2 revolutions, REV, not to be confused with that, 2 pi radians per revolution, and we multiply that by 1 minute per 60 seconds, then we see that we have pi over 30. And we see that revolutions went away, minutes went away, and this is radians per second left over. All right, well, so that translated into English, if we remember that number, then whenever we see 1/800 radians per minute, and we multiply it by pi over 30, we will get an answer in radians per second, which is what we need. So 3 goes into there 6 times, so it's 600 pi radians per second, and 2200 revolutions per minute times pi over 30 gives me what? 3 doesn't go into that anymore, does it? 200. What's going on here anyway? No one's complaining about that extra 0. Anyway, we need to complain about those things. 220 over 3 pi radians per second. So now that we have our revolutions per minute in radians per second, now we can find our alpha, which is going to be the change in omega, which is in radians per second divided by change in time. Well, change in time is easy. It's 10 seconds. So I'm going to divide by 10 seconds. And now, what do we have up here? We have 220 over 3 pi minus 60 pi divided by 10. And when we get done, we know our answer has to be in radians per second squared, because alpha is acceleration, and acceleration is per second squared. And all right, so what are we going to do about that? 220 divided by 3 minus 60 equals divided by 10 equals, we'll change it back to a fraction, 4 over 3 pi. And then we'd say, well, is that good enough? We have 3 significants in our answer, 3 significant digits in our answer, so we'd probably want 3 significant digits here, times pi 4.19. 4.19 radians per second squared. Should we check our work? All right, initial velocity plus initial angular velocity plus 149 times 10 equals, okay, so 60 times pi plus 4.19 times 10 equals 230 point something. All right, now that's radians per second. All right, so this is in radians per second. So we multiply that by 30 over pi. 30 over pi to change it back to RPM. Okay, so times 30 divided by pi, and I have 2200 RPM to 3 significant digits anyway, which is exactly what I started with, so I must have got it right. All right. So we covered chapter 9 in the physics book, which will be a next semester thing, and we covered chapter 4 in the physics book too. So the translational moving things with the X's and the V's and the A's, that was chapter 4 in the physics book. With the alphas and the omegas and the thetas, that was chapter 9 in the physics book. Okay. We do number 19. Now, number 19 is one of those where the instructor could get lucky and could get it right, or it could take the rest of his natural life to get it right. It's hard to say. All right, so we need 2 circles, a smaller one and a bigger one. Okay, and then we got a hook of rope going around those circles. All right, so that looks good. And we're going 1, 2, 5, 0 RPM on the little guy. All right, and we have 2 meters. 2 meters, that's huge. 2 centimeters. All right, that's not as huge. We have 2 centimeters. Okay, and the big guy, B, we have 8 centimeters. And the author has given us A, B, and C to answer, so with a little bit of luck, if we go through A, B, and C, put them in the right order. Now, sometimes the author will put A, B, and C down, but you have to do C before you can get the A answer. But normally that's only in the physics book. In the tech math book, we normally can go in order. So, question A says, we want the linear velocity of a point on the rim of pulley A in meters per second. All right, so is it, this is A. So is the question written in English? That's the first issue. Yes. Does it make any sense at all? No, of course not. All right, so, but what do I know? I can go and take 1250 RPM and multiply it by pi over 30, and I can get radians per second, which is what I want to know. So 1250 divided by 30 divided by pi divided by pi multiplied by pi multiplied times pi. So I've got 130, we'll call it 131. And I have 3 significant digits. Okay, so I'm only going to go with 131. 131 radians per second. Now, if my sector length is r pi, then what do you think the velocity is going to be? It's not r pi though, it's r theta, right? R theta, then the velocity has to be r omega. 2 times 131 radians per second. 2. That's not right. Something's not right there. Right. This is centimeters per radian. All right, so if we think of the radius as 2 centimeters per radian, and then we multiply that by 131 radians per second, then we can see my radians go away and I come up with centimeters per second, but I want my answer in meters per second. So that means I'm going to go and divide, going to multiply by 2 and divide by 100. 2.62 meters per second. Okay, so now I've got A, the velocity of the guy at A. Okay, excellent. Anybody disagree? Other than, now, normally, if I had long sleeves on, there'd be something on my sleeve, I'd be hiding it, right? Am I hiding anything? All right, so I'm not on purpose? Is it almost time for our song? All right, no, not time for the song yet, okay. All right, now, part B. The linear velocity at a point on the B rim. Okay. All right. The linear velocity on the B rim. If the rope is moving 2.62 meters per second on the A guy, how fast must it be moving on the B guy? The same, right? So the velocity on the B guy has to be the same, 2.62 meters per second. Well, that was easy. Find the angular velocity on the B guy. Okay, now that's of course of a different color. Alright, so C. Alright, so I said that velocity B is going to equal r omega. Okay, so I know velocity B, 2.62 meters per second. I know the radius would be 8.00 centimeters, which doesn't do me any good at all. So I'm going to change that to meters before I even go anywhere else. 0.08 meters times omega. Okay, well, looks like one equation, one unknown. I guess I'll just put it in my calculator and tell me what the answer is. I will? Yeah, sure. Second function solves something numerically. All right, so I've got 2.62, and that's equal to 0.08 times x, because I don't have an omega key. Thank you very much, calculator, for getting rid of everything for me. And it says x is 32.75. So omega is going to be 32.75 radians per second. Now I would expect, now you can just go and divide, right? Just divide by both sides. We're just showing our friends that our calculator can do that too. All right, that's wrong, right? So then put that down, that'd be wrong. Minus 0.1 significant digits, because we only have 3 significant digits. So that means we better round it up. 32.8 radians per second. Anybody have their book open to see if we're right? We're right? All right. Darn right. That is so disgusting when that happens. Okay, questions about that? No? Okay, so we're done with chapter 10. The plan is tomorrow we review for the next test, and on Friday we skip the quiz and go right to the test. Okay?